Hi, my name is Nathan Walters. I'm here to present on Harmonize, a framework I've worked on for secure federated learning. Let's begin. We're going to approach this through the framework of a case study. We've got a lot of individual case studies that want to determine whether the immunoglobulin CD147 is a good indicator of prostate cancer. We would like to, now these individual studies are very small, so we would like to be able to share information between several of them. The trouble is these are sensitive medical records, and from both a legal and a moral point of view, we need to make sure that we keep them well protected. A common tool for this is differential privacy. It's a proven technique for defending individual records from de-anonymization attacks, and it works by adding a random noise element during the learning period. The trouble with this, for our purposes, is we have many contributors, each of which is adding their own level of noise, and it adds up very quickly. You get something very noisy. In this case, that's going to correspond to our model losing performance because the data has so much noise added to it. To combat this, we're going to look at homomorphic encryption. It's going to allow us to add up encrypted data. So that means we don't have to add as much noise because everyone individually can add a small amount. It adds up in total to enough noise to protect us using differential privacy, but not a lot more. In order to make sure this is extra secure, we're also going to make sure that this requires collaboration in order to decrypt. From a bird's eye point of view, what's going to be happening is we're going to have one central conductor that is going to be running the operation and multiple clients. In this case, the clients are the individual studies. And in practice, all of these are instances out in the AWS cloud. So what's going to happen is the conductor is going to send out a query to all of the clients, and they're going to query their own data, and they're going to add a small amount of noise. They're going to encrypt these responses and send them back. Because this is homomorphic encryption, the conductor is going to be able to put these together into an aggregate, and it's going to then send this back out for decryption. The clients are going to work together to decrypt it, send that back to the conductor, who's going to finally put them together and come up with a clear text aggregate. In practice, what does this look like? So over here, we've got TuneUp. That's what I'm going to run to make it so that all my clients, as well as a key generator, start up and are listening. They all have their own local MySQL files that we're going to be looking at. Then I'm going to run Harmonize. The conductor is going to talk to all these clients and the key generators, and it's going to give us this final value of an odds ratio, 6.31. Now, it turns out that 6.316 is about the correct number, so we got an excellent result from here. But this is a stochastic process. You can randomly get a better or a worse result. So how do we do when we try many cases of this? Well, I tried 30 using regular differential privacy and 30 times using Harmonize, and here are the results I got. We see that using pure differential privacy, when we're adding more noise, gives us a much wider series of responses, including one very nasty outlier that's off by more than the value we're even looking for. Whereas Harmonize consistently gives us values close to what we're looking for. In fact, we reduce the variance of these responses by a factor of more than 14 when we use Harmonize. All right, so a little about me. My name's Nathan Walters. I have a picture up here of me as a harpist because I consider myself a tool creator, and I consider Harmonize a tool where you spend a lot of time making a tool that's going to be used only for a few seconds. And that's a lot like being a musician, where practicing for 10, 15 hours for a 5-minute piece of music is actually considered a very good trade-off. Here I also have a couple of universities I've taught at, and I bring up the game Hanabi because it's a problem I worked on that I'm very proud of, where I taught a computer to play the game and how to communicate with itself more effectively. All right, that's been my presentation. Thank you for listening.